Merhaba arkadaşlar. Geçen hafta ne işledik? Rotate'ler vardı hatırlarsanız. Rotate left, rotate through, carry left, rotate right, rotate through, carry right. 3 örneğimiz vardı. 3. örneği ödev olarak vermiştim. Utku rotate kullanmadan yapmıştı. Gönderdi bana. Onun dışında neydi? DX, BX, AX üçlüsünü tek bir register'mış gibi düşünüp bir hexadesimalde bir karakter ya da 4 kere sola kaydırmamızı istiyordu. Şimdi şu cevabı şuradan alayım. Cevap üstünde anlatacağım. DX, BX, AX. Yani en solu bu. A, B, C, D, E, F, 1, 2, 3, 4, 5, 6 da AX. Bunu sola kaydırdığımız zaman ne olacak içerik? Bunu anlatmıştım. İşte B, C, D, E, H, DX de olacak. F 1, 2, 3, H, BX de olacak. 4, 5, 6, A. AX de olacak. Bu baştaki A sona gelecektir. 4 kere kaydırmanın sonucunda. Bunu nasıl yapmışız? Döngümüz var. Kaç kere döneceğimiz belli. Loop kullanmışız. Niye buna 2 demişiz bilmiyorum. Öncelikle DX, BX, AX üçlüsünün sola doğru kaydırdığımız zaman soldaki DX'in the most significant bitini, en önemli bitini kaybetmemek için rotate left deyip carry'e düşürüp rotate right deyip geri alıyoruz. Sonrasındaki bu 3 işlem asıl kaydırma işi. A'yı B'ye, B'yi D'ye kaydırma işi. A'yı bir rotate, B'yi bir rotate, D'yi bir rotate. Ama bu rotate'lerde arada carry olduğunu düşüneceğiz. Mesela şöyle düşünün. Şu arada carry var. Carry'yi kullanıyoruz şeklinde düşünün. Aynen. A'yı RCL deyip sola rotate ettiğimiz zaman most significant biti 3 değil de most significant biti hexadesimal değil binary biti carry'e düşüyor. Sonrasında bu RCL'i kullandığımız zaman o carry B'ye giriyor. B'nin most significant biti değil de most significant biti carry'e düşüyor. Sonra tekrar RCL'i kullandığımız zaman o D'ye giriyor. D'den çıkan burada D'den çıkan burada içeri sokuluyor tekrar. Böyle emulate edersem daha güzel anlaşılacak sanırım. Tabii başka çözümleri de var. Böyle kısa bir çözümünden bahsetmiştim. Nereye açayım? Bunu açarsam tek tek bakmam lazım. Şöyle açtım. Böyle bakabilir miyim? TX'e bakalım. Word şeklinde binary versiyonuna bakın. Rotate left dedik. Diyeceğiz. Carry'i de açalım. Flag'lerden. Rotate left dedik. Carry flag'e düştü. Geldi. Rotate right dedik. Bakın carry'i aldık. Most significant bit'i carry'e aldık. Sonrasında yaptığımız AX'e gidip bakalım. Rotate left diyeceğiz ya arkadaşlar. Bu carry buraya sağdan girecek. Binary'nin en sağına bakın. Bu carry sıfırlandı, sağdan girdi. Carry sıfırlandı derken bu arada bunun most significant bit'i carry'e düştü. Aslında carry sıfırlandı değil de most significant bit'i carry'e düştü. Şimdi AX'in most significant bit'i carry flag'te 0. Bu sefer de rotate through carry left BX dediğimiz zaman BX'in en sağına bu carry girecek. 0 girdi. BX'in en solundaki 1 de carry flag'e düşecek. Şimdi DX'e geldiğimiz zaman carry flag en sağdan girecek. Most significant bit de carry flag'e düşecek. Carry flag'imiz 1. Loop başa dönecek. Başa döndüğümüz zaman bu artan kısmı rotate left deyip sonra rotate right deyip içeri aldık. Şu an bir döngü tamamlandı. Bir bit döndük. Bunu 4 kere yaptığınız zaman sonuca bakarsanız Zoom programını açmamışım. Ümit miydi? Yapma. Neyse. Sonuca bakarsanız BC, DE, F1, 2, 3, 4, 5, 6, A. Sonucumuz bu. İnceleyin arkadaşlar bu cevabı. Kurcalayın. Neden böyle olduğunu anlamaya çalışın. Güzel soruydu çünkü. Şimdi sorusu olan var mı? Onu bir sorayım. Yeni haftaya başlamadan önce. Evet, çok geniş geliyor ya. Bunu kapattık. Okay, let me switch into English. Today's topic is stack. We are going to implement stack with push and pop commands. In emulator, please remember we have some registers at the left. One of the registers are let me zoom now. Stack segment, stack pointer. Please be aware that this is a combination like this, address combination, a couple. We keep mentioning about the couples. Data segment, source index, exit segment, destination index couples, code segment, instruction pointer couples. And this is the stack segment, stack pointer couple. Okay. It is showing the top of the stack. Okay, let me open the tutorial of stacks for you. Stack, let me zoom a little. Stack is an area of memory for keeping temporary data. It's an area of memory. We call them stack, but actually that's a memory location. Stack is used by call instruction, blah, blah, read instruction, blah, blah. That's not important for now. We can also use the stack to keep any other data. There are two instructions that work with the stack. Push instruction stores 16-bit value into stack. Pop instruction gets 16-bit value from stack. Okay, syntax for push. Let me open the push instruction. Open push instruction. Okay, push instruction. It gets only one parameter. Register, S register, memory or immediate. In our 8086 architecture, it doesn't allow immediate. Push immediate works only on 186 CPU. So our emulator can support, but in our lab session, we doesn't accept immediate. So just know that register, S register or memory we can push to stack. Okay, what does this command do? This command algorithm updates stack pointer by 2 by decreasing the stack pointer. Let me write a simple code. Okay, when we emulate this, we have a stack button. Okay, this shows the stack. It starts from the combination of stack segment stack pointer 100 and FFFE. When we write this address, we can see that, by the way, every line within the stack is 16-bit. It goes 2 by 2s. But remember, our emulator shows 8 by 8. So these 2 lines represents this single line. So FF0 is our starting value. From that point, if you use a push command, for example, with AX, and another one with, for example, CX, we can see the stack. For example, stack is updated. We push AX into FFFC location and CX into FFFE location. Okay. Stack segment is same. Stack pointer is updated with -2. It decreases. Stack segment stack pointer combination shows the top of the stack. Okay. It calculates the position where stack segment stack position stack pointer showing and put the operand 16-bit operand value in there. That's it. Let me open the pop also and write a meaningful, for example, we have values like this. I'm going to push AX, push CX, push AX again, push CX again. Okay, let me show you the stack. Okay, we put 1173, 8086, 1173, 8086. Stack pointer shows the last location used. In pop algorithm, stack pointer is increased. In push algorithm, stack pointer is decreased. In push, it decreased first, then put the value into stack. In pop, it gathers the value from stack, then increase. It is important. Let me open this into push. Let me open pop here. Okay. Push, decrease the stack and put the value. Pop, get the value and increase the stack. The main difference is this. Let me use pop from here. I'm going to get a value from the stack and get the value into dx and another value from stack and put it into bx. Okay. I put 1173, 886, 1173, 886. Okay, this is the, you can see the arrow. This is the location of stack segment, stack pointer pointing. Okay, now I'm going to make a pop. It will gather a 16-bit value from the stack, which is 886, and put it into DX register. Okay, DX is now 886. Now stack is updated. The current value of stack is FFF8. But keep in mind, the previous value is not deleted. We just update the stack pointer. We use the memory. Okay, another pop bx command, which will update bx with 1173. And as you can see, previous values are still there. You can go and look, by the way. Okay, this is the head of stack. We put the first value, put the second value, put the first value again, put the second value again, pop this value to dx, pop this value to bx, and the current stack pointing to here. If you update, it will go here and gather, because in pop it updates text first, then gather the value. Okay, that's it. Let me open the tutorial. And what it is saying, it shows the syntax of push and pop. Push and pop work with 16-bit values only. Okay, we already mentioned that. Push immediate works only 186. Okay, we already covered that. Okay, now stack. Stack use a last in first out algorithm. Stack is like this. By the way, if you use last in first out algorithm, it's called stack. Stack can't be used with any other first in first out algorithm. You have to use last in first out algorithm in order to it be called stack. Okay, this means that if we push these values one by one into stack 1, 2, 3, 4, 5, and the first value that we'll get on pop will be 5, then 4, 3, 2, 1. Okay, this is last in first out algorithm. It's very important to do equal number of pushes and pops, otherwise the stack may be corrupted and it will be impossible to return to operating system. As you already know, we use return instruction, blah blah blah. Push and pop instructions are especially useful because we don't have too much registers to operate with. So here's a trick. Store original value of the register in stack. Use register for any purpose. Restore the original value of register from stack. Okay. It gives a simple hint for stack usage. We don't have too much registers. We can use memory location of stack by using push and pops. For example, it gives an example. We have an 1, 2, 3, 4 value in AX. We push this value into stack and make some calculations over AX. After some calculations, we pop the AX back and restore the original value of AX so that we doesn't lose the original value of AX. Another use of the stack is for exchanging the values. Remember, we use temporary variable in order to exchange values. AX, BX, for example, CX. When we want to change the AX and BX, we copy AX into CX, BX into AX, CX into BX. This is old-fashioned. You can use stack. For example, push AX, push BX, put this value into stack, and pop AX first and then BX so that AX and BX will be switched. The exchange happens because stack use last in first out. So when we push 11, 12, 12, and then 13, 34, and pop will first get 34, and after it will get 12. Stack memory area is set by stack segment. Please remember, stack segment is a segment. If you want to change the stack location, for example, I'm going to use AX and update the stack segment as 200. Okay, now stack segment is 200 FF. When we open the stack, as you can see, stack's location is here. Generally, operating system sets value of the register on program start. Subtract 2 from stack pointer register, write the value of source operand to this couple. Pop, we already covered the algorithm. The current address pointed by stack segment stack pointer is called the top of the stack. This is important. The current address pointed by stack segment stack pointer couple is called the top of the stack. For COM files, blah blah blah, you can visually see the stack by clicking stack button. The top of the stack is marked with arrow sign. Okay, this is a tutorial for stack usage. We cover the stacks. There are other push and pop commands. I'm going to cover them also. For example, pop A. It doesn't take any parameters. It stores all the registers into stack with a single pop A command. Let's start with push A, not pop A. It stores all the registers into stack without any parameters with a single command. For example, let me push A in here. This is stack. I have updated the AX, which is 200. I'm going to store all the registers within this left-hand side into stack with a single command, push A. Okay, stack is updated. There are some values here, as you can see. What are the values we are pushing into stack? These are A, C, D, B. There's a different order other than A, B, C, D. It is starting from AX, CX, DX, BX. The order is important. After that, stack pointer, base pointer, source index, destination index into stack. Original value of stack pointer is used. This instruction works only on 186 CPU, not our 8086. It's a useful instruction. Just know that, for example, after all of this things, not using any push or pop commands, I'm going to pop A and restore the AX and CX value in here. Let me show you. Okay, AX is now 1173, CX is now 8086, but we have stored the original values of these AX and CX, which was 200 and 0. When we pop these values from stacks, the left hand side of these registers will be updated, and as you can see, AX is 200, CX is 0. Okay, by this way you can store all registers within this order into stack. Okay, another one is push F and also pop F. This one is also useful. Where does it get? Push F. It's a single command. It stores the flag register into stack. Remember, flag register is a 16-bit register with some of its bits are flags. Actually, it's a 16-bit a single register. When you use a push F command, it stores the current flag positions into stack. Let me for example, I'm going to set carry and push flags into stack. Get rid of this. Clear carry. Sorry. Clear carry. Push the flags into stack, and after that pop the flags pop F command. It keeps updating itself. Pop F command. We'll gather it from the stack. Okay, let's see. Open the flags first. Open the stacks also. Okay, we set the carry flag with stc command. Set carry flag command. The current values of flags are like this. We push these flag positions into stack. Okay, as you can see, the flag register is 300 and 203. This is the current 16-bit register of flag. We make some calculations, update some values, and for example, clear the carry flag. Flag positions are now like this. And I'm going to restore the original values of the flags with pop F commands. As you can see, carry flag is returned. This is used for that. Okay. Any question? Any question about stacks, push, pop? Okay. Then we have a single question, single example, which is a Fibonacci question. Calculating the first 24 Fibonacci numbers and store the numbers in descending order in memory starting at 2000 H memory address. We need to calculate the Fibonacci numbers. Let's open program. We need to make Fibonacci numbers with text, by the way. We need to cover this example with our topic of stack. We have a constant value 24. That's why I'm going to use cx 24 and a loop that runs 24 times. Okay. Within the loop, I'm going to find the Fibonacci numbers and push these Fibonacci numbers into stack. After the loop, after the loop, I need another loop. Yes, I need another loop. Let's say 2 this time. Because this time I'm going to get the value from stack and put it into memory location. I need to run again 24 times. I'm going to pop value from register into something like, for example, AX, and put this AX into memory. location of 2000H. But I need to increase this 2000 location word by word. I can use source index and add source index to this way. But I have also another command which stores AX into, stores, let me open the errors, push errors, wrong parameters because it doesn't have a semicolon. Okay, please remember that we have couples, exasegment, data segment source index, exasegment destination index. Yeah. So when we're writing using STOS word, we store into exasegment destination index. I'm going to use exasegment destination index couple to use STOS word. Let me open the STOS word command for you. It puts AX value into exasegment destination index. Before using here, I'm going to update exasegment, for example, with AX, and also update destination index, which is 2000H for now. In order to update exasegment, what is exasegment in question? Oh, it doesn't change the segment. It uses the default segment. So I'm not going to change exasegment. I'm only going to change destination index and use a source word. Okay. This is the second loop. That's more than enough. Let me open this door. It's more than enough. Okay, the first loop. The first loop is here, the second loop is here. The second loop gathers the value from the stack, which is in descending order. We have covered the Fibonacci number starting from the 0 to 24th Fibonacci number. So at the top of the stack, we have 24th Fibonacci numbers. So when we pop the last element from the stack, we gather the maximum, the biggest Fibonacci number we have. Yeah, that's the correct usage. We pop and stores word, pop and stores word. This will run 24 times. There's some... Oh, Ibrahim, good catch. Descending order in memory. It doesn't explicitly state that. It says descending order in memory starting at 2000H. If it says address, it should be like this, but it didn't say address. So you may be right, Ibrahim, but it's not that important. But thanks for the catch. Okay, this is the second part. Second part is saving Fibonacci numbers into memory. Okay. We need the first part, calculation of the Fibonacci numbers. Let's open Fibonacci numbers first. Who knows how to calculate Fibonacci numbers? Give me the first number of Fibonacci numbers. Oops, I opened already. What is the first number of Fibonacci numbers? Any idea? Utku says 1. Berke says 1. Ibrahim says 0. That's the question I keep asking to students, but I also don't know that. I keep Googling that. The Google says it starts from 0, but it's up to you, because please remember, if you start from the 0, the second number will be 1. We add this together, it will be 1. Add the previous 2, which will become 2. Previous 2, 3, 5, 8, 13, 21, goes like that. Okay. It doesn't actually that matters. At some point this fractal should finish. So I think it should be 0, but some source says it starts from the 1. Okay, all of you are correct, that's why. From here I'm going to use BX and AX registers, the first two Fibonacci numbers within AX and BX, and calculate the other numbers with these two registers. Okay, let's first push the first two Fibonacci numbers into stack. I'm going to push AX first Fibonacci number, second Fibonacci number. Okay, now I need to calculate the third Fibonacci number. That's why this loop shouldn't run 24 times. It should run 22 or 23rd times. Let's say 23rd. But the second loop should run 24 times, because we have the numbers at the beginning. Okay. We need to calculate some Fibonacci numbers and push it into stack. How can we calculate the Fibonacci numbers? We need to add these two numbers. It's a bit obvious. AX, BX. Now I have the third Fibonacci number in AX. Now what? In order to run this loop in correct way, I can push AX directly. This is the third number. But then it will keep adding BX into AX. BX is 1, it will increase 1 by 1. Let's emulate this one and see the stack. I want to change the stack location, because at the beginning of the stack location there's FF00. I don't want to see that. Okay, let's change the stack location into 200H. Update the stack segment with AX. Okay. Now never mind that two lines. Emulate this. Okay, stack location is like this. We have AX0, BX1, push AX, this is AX, push BX, this is BX. These are word by word, this is AX, this is BX. Okay. Now, we add them, 1 plus 0, which is 1, put it into AX, AX is now 1, and push this AX into stack. Okay, the third Fibonacci number is 1. Now we need to find the fourth Fibonacci number. Fourth Fibonacci number is 2. We need to add the previous value of, it will calculate correctly, but actually not. Okay, the fourth Fibonacci number is 2. The fifth Fibonacci number will be 3. Okay, now BX is 1, AX is 2. By adding 2 plus 1, it will calculate 3 and push it into stacks. By this way, it will push incremental values into stack, because we keep adding BX. We need to update BX after push or before push, does it matter? We need to change BX with previous value of AX. So I need to change bx with the previous value of ax. Is this correct? Let's see. It's a bit complicated. Every time I try to run Fibonacci numbers, I keep forgetting the algorithm. Okay, we add, let's open stack and see if it's correct. It goes like this, 4, 8, 10, it goes but in a wrong direction. The numbers should be 0, 1, 1, 2, not 4 but 3. So where we make error? The calculation of 2 is wrong also. In the first example, let's dive into here. 1 plus 0 is 1. We push this value into stack. AX is 1. We put AX into BX. We also store the AX value, previous AX value. Yeah. We put BX into AX, AX into BX. Push the previous value into something different. AX value into DX. AX into DX, not BX, right? Then EX into AX. After that, we push DX into BX. Is this correct? At the end of this algorithm, I need to push Let me check. I write something. I don't know. Yep. This is correct. 1, 1, 2, 3, 5, 8. D. D is 13. This is hexadecimal. Okay, this is correct. You can also find it on your own. I make some switches. This is the first part. It calculates the first, 23rd Fibonacci numbers. By the way, I update this question with 24 because the maximum Fibonacci number that can as word can store is 23rd value of Fibonacci. 25th value of Fibonacci is bigger than a 16-bit value. That's why we make easier this question. After that, we need to put this in the memory. Let's emulate and run till it ends. Okay, some stores words. Oops. Why it turning back? There's something wrong. Stores words. Pop into AX stores. Destination index is 2000. What's wrong? Something wrong. Let's emulate the first part first. Cx will be 0. Okay, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, now when I open the stack, I can see the numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Oh, it calculates more than. That's why we need to decrease this number. It starts from the beginning. At the end of this loop, maybe we need to return correctly, return to operating system interrupts. What was that? It was, I couldn't remember. 4C. Yes, 4C. 4CH and interrupt 21H. Program has returned to control the operating system. Let's open the memory location of 2000 of default address. Okay, starting from here to here. This is most probably the location of 200H. I wonder, I'm just going to change this into 500 and write the previous code. I'm just wondering if it is the case. No, it's not the case. Okay, question is this. The first loop calculates the Fibonacci number and push it into stack. The second loop pop a value from the stack and put it into memory. Memory location is 2000H or 1000H with 100 segment. It doesn't explicitly mention it in the question. Any question? Ibrahim has another solution about what? Pop AX, Pop BX. Sorry, Ibrahim, I couldn't see your answer. This is my answer. The first part. You need to push only once. You push more than once. You need to find the Fibonacci number and push it into stack. If you make this loop within this loop, you push more than once. So this will be wrong. Okay, another question. By the way, this can't be the only solution. You can find your own solution also. I'm stopping this recording here. If there is any question, please feel free to ask.